Hey guys, okay, so this question is for the midterm review, and it is question number 82 from chapter 4. So basically this question is about a ball bouncing down a 20-degree inclined slope, and it says the distance between the bounces is 3 meters, and it wants us to determine what's the velocity after this first bounce. So as soon as this bounces, what's the velocity? And the first thing I'm going to do is I'm going to go ahead and tilt my axis so that it's along the tilt of the plane. So I'm going to start by doing that, and we know that that is going to be 20 degrees, right? So then I know that the degree, so theta of the ball, so the angle that the ball makes after it bounces with respect to the tilted plane is 70 degrees. But for the purpose of this problem, what I'm going to do is I'm going to try to keep it as simple as possible and make a horizontal plane. So my x-axis is horizontal and my y-axis is perfectly vertical. So over here I know that this is 20 because that incline right there is 20. So I know the angle that the ball makes after the first bounce with respect to a perfectly horizontal origin has to be 70 minus 20 or 50 degrees. Now that's a little bit confusing, I know, I understand, so I would rewind and see how I got that again if you're still a bit confused on that, but that's how you get 50 degrees. Now I'm going to set up some relationships. So the first thing I'm going to do is I'm going to try to find, so since this is delta x, right? That's delta x to 3 meters. I want to try to find this delta y right here. And I think the easiest way to do that is going to be, so tangent of 20 degrees is going to equal opposite over adjacent, so delta y over 3. So I know 3 tangent of 20 degrees is going to equal delta y. And you should get delta y equals, so remember delta y you would get a positive number, but since I know, I'm going to define down as my negative and up as my positive and right as my positive, left as my negative. I know that that delta y is actually going to be negative 1.09 meters. Okay, now that I have that, I'm going to set up another relationship, which is that my velocity initial x, so the x component of the velocity of the ball, is going to equal my change in x with respect to change in time, so dx over dt if you want to call it, which is going to be 3 over change in time. Okay, now I want to try to get this, since we know our change in y, and I know that the acceleration is going to be impacted by gravity, I want to try to get my velocity initial y in terms of t, so that way we can solve for a t, and you'll see what I mean later on. But so what I'm going to do is I'm going to set up a relationship between, so I want, what's the relationship between the velocity initial x and velocity initial y? And I think, so what I'm going to do is I'm going to say tangent of 50 degrees, right? And remember, 50, it's 50 because that's the launch angle with respect. So that's the launch angle. I mean, I'm calling it launch angle, it's actually the bounce angle after the first bounce. But it's going to equal, so if that's 50, it's going to be velocity initial y divided by velocity initial x. And I'm going to get that my, so velocity initial x is going to equal velocity initial y divided by tangent of 50 degrees. And I'm going to go ahead and take this and substitute it in for there. So I'm going to substitute that in, and I'm going to get, I should get velocity initial y divided by tangent of 50 degrees is going to equal 3 over delta t. I'm going to multiply that over, so I should get velocity initial y is going to equal 3 tangent of 50 degrees divided by delta t. I'm sorry, that should be, let me go ahead and erase that. That should be delta t, right? Because there's a delta t there. I just messed that up. Okay, so that's that. Now I can go ahead and start writing out some of my kinematic equations. So I know my y final is going to equal y initial plus velocity initial y t plus 1/2 ay t squared. I'm going to go ahead and substitute velocity initial y in for here, and you know my ay is negative 9.8, and I'm going to try to solve for t. So once you do everything, you know, and I know my y final, right? So I'm going to get negative 1.09 is going to equal 0 plus velocity initial y, so it's 3 tangent 50 over time. I'm going to multiply it by time again, so the times cancel, so it's going to be 3 tangent of 50 degrees plus 1/2 times negative 9.8 times t squared, right? So t squared, that's going to be 9 tangent squared 50 degrees over delta, oops, no, where is that? 9 tangent squared, oh wait, what did I do? Oh, sorry, I should not be substituting in. That's my fault. That should just be times delta t squared, right? So times t squared. And I can go ahead and solve for t. When you solve for t, you should get that your time is going to equal 0.976. So 0.976 seconds. Now that's my t. Now I'm going to go ahead and go back and try to get my initial x and initial y. So if I go back here, I know my velocity initial x is going to equal 3 over change in time, which we know now is 0.976. So you should get, that's going to be 3.07 meters per second. And my velocity initial y right here, so velocity initial y is going to equal 3 tangent of 50 degrees over 0.976, right? That's coming from over here, delta t. And that should equal 3.66 meters per second. Okay, so we're almost done, and I just want to point out, so right now we've got velocity initial y and velocity initial x, right? So my velocity vector along the x component and my y component, and basically we're trying to solve this total component right here. So I'm just going to use the Pythagorean theorem, and I should get, so it's going to be the square root of velocity initial x squared plus velocity initial y squared, and I know those numbers, right, so I can fill those in, and you should end up with 4.7 meters per second. That is the answer.